This is Christa McAuliffe, live from the Challenger. Teachers are excited about this.
Alka-Seltzer in the container.
Look at that bubble!
Here's your reaction.
The whole country was invested in that mission. We're going to have the opportunity to kind of bring that mission full circle.
Hi there, my name is Serena Anand-Chancellor.
And I'm Ricky Arnold, and we are living and working on the International Space Station. Today we're going to look at Newton's 3 laws of motion. These laws tell us how all motion behaves under ideal circumstances. Since we are in microgravity, we may be better able to show you how these laws work compared to if you try these demonstrations back on Earth.
Let's start with Newton's first law of motion. An object in motion stays in motion, and an object at rest stays at rest until another force acts upon it. So here you can see a ball full of candy. Let's release this ball and let it float down the entire module. Normally, on Earth, this ball will eventually fall to the ground because of gravity. But up here, since we don't have gravity acting on us, or really microgravity, that ball will continue to go for a very long time.
The air in this module also generates friction, which is a force slowing the ball down very gradually. In fact, we use the friction of our atmosphere to slow our spaceships down when we land. However, if I took this ball out on a spacewalk in deep space and did the same thing, it would keep on going forever, or until eventually, maybe it collided with something.
Hey, I'm working here.
Let's look at Newton's second law of motion. It says a force is equal to the mass times the acceleration of an object. If you put the same force on 2 objects, one with a large mass and one with a small mass, which do you think will accelerate faster? Let's see what happens. You can see Ricky on one end of the module, and he's got 2 bags with him. These are bags we often use on space station to stow lots of items. In one bag, he has bubble wrap, very, very lightweight, well, really light mass. And as you see, as he releases that bag of bubble wrap, it really flies quickly down the module. In the second part of the demonstration, he has the same bag, but this time it is filled with water. We have a much higher mass that we're dealing with here. Even though Ricky exerts the same force on it as he did with the bubble wrap bag, you can see how much more slowly that bag of water moves down the module. And that is Newton's second law. Finally, let's look at Newton's third law of motion. This says that for every action, there is an equal and opposite reaction. If I put a force into something, it is also putting a force back onto me. Let's see what this looks like up here in microgravity when I push on 2 bags. Remember, one is filled with bubble wrap and the other with water. As you can see here, when I push the bag of water, it exerts a force equal and opposite back on me, and it looks like it's almost pushing me backwards. But when I push the bag of bubble wrap, I remain almost virtually still, just spinning ever so slightly. Can you see the difference? So as you can see, Newton's 3 laws can describe all movement. Now it's your job to see what these laws look like on Earth. Start thinking about what might be different and why. Thanks for participating in our experiment today. Signing off, I'm Serena Anand-Chancellor.
And I'm Ricky Arnold. See you next time.